Good morning, everyone. This is Shauna, and I'm coming to you this morning with part two of the 4.1 sample spaces video. In this video, I'm going to start by talking about the types of probability, and then I'm going to talk specifically more about the sample space for a deck of cards and hopefully for two dice. We'll see how far we get. Okay, let me share the screen at this time. And as you recall, last time we were talking about, let me make sure I can hold this up where you guys can see it. Yeah. Okay. We were talking about probability, and we said that it was a chance process. We said that we have trials, we have sample spaces. This is something that you're going to be seeing a lot of in the next few sections. This is a deck, a standard American deck of cards. It's reproduced here for you. Before we start talking about the deck and how it works, the sample space, remember, is all possible outcomes of a probability experiment. But I'd like to spend some time going over this. So we have different types of cards, as you can see here. Let me do something here with this. Whoops, that's not what I wanted to do. Okay, what I'm gonna do is she's shown you that there are 4 different types of cards. 2 of them are black and 2 of them are red. Each of those types of cards has a name. So these things that look like black 4-leaf clovers or 3-leaf clovers are called clubs. Those are clubs, okay? The ones that look like black hearts but upside down are called spades, okay? The ones that look like Valentine hearts that are red are in fact called hearts, okay? And the ones that look like red diamonds are in fact called diamonds. So clubs and spades are black, and hearts and diamonds are red. Okay, that's just how it is. No matter what else, what other colors you might see on the cards, no matter what deck you might be looking at, hearts and diamonds are considered red, and spades and clubs are black. Now, those are suits. So there are 4 suits of cards. Clubs is a suit, spades is a suit, hearts is a suit, diamonds is a suit. Now, within each suit, we have the same types of cards. This thing that has an A on it is an ace. Then we have 2, 3, 4, all the way to 10. And then we have these 3 cards with people on them. We call them face cards. So there are 12 face cards total in the deck. There's a jack of hearts. Sorry, a jack of hearts is down here. There's a jack of clubs, a queen of clubs, a king of clubs, a jack of spades, a queen of spades, a king of spades, a jack of hearts, a queen of hearts, a king of hearts, jack of diamonds, queen of diamonds, king of diamonds. Okay. These cards that have people on them are called face cards. So there's 12 of those, 3 in each suit. Okay. 3 in each suit. Now, aces are interesting. In most of the problems in this class, we consider an ace a value of 1. So it's lower than a 2. There are a few problems that ace is considered a high card. So you might hear the phrase ace is high in some games. That means that an ace is actually considered like an 11, and why is it an 11 or maybe even a 14, depending on how the game is played. Sometimes the ace comes after the face cards, and these are all 10s. So a lot of times the jack, the queen, the king are all 10, and then the ace is an 11. So aces can usually be ones if they're ace low, or ace high would mean that it was generally an 11. If it was something else, they would have to tell you. But just so you know that, you'll hear this phrase standard deck or ordinary deck. The reason for that, and we don't have a picture of this on this screen, but if you go to a game shop, you go to the 99-cent store, you buy a deck of cards, you might get a deck of what we call 54, which is standard. There's 52 cards on this screen, 13 cards in each suit, 4 suits, there's 52. The deck you're going to buy is going to have what we call 2 jokers in them. And jokers are people like these face cards. They're people, but they're in funny costumes with like a clown outfit and those pointy shoes. Those are jokers. And in some card games, if you are into playing American card games, jokers are used as wild cards or used for other things. But an ordinary deck means we've removed the jokers, we've taken them out. So we're dealing with just these 52 that you see on the screen. Okay, so we're dealing with a standard or an ordinary deck of 52. So once again, suits, there are 4 of them: clubs, spades, hearts, and diamonds. The actual types of cards, the aces, the 2s, the 3s, the 4s, all the way to the kings, those are called ranks. So the ranks are the individual values of the cards: ace, 2, 3, 4, jack, queen, king, something like that. So just some things to be aware of as we look at some card probabilities here. Now, I'm going to switch at this time, and I'm going to go to our homework in sample spaces. And I'm going to come back to number 6 and okay, the dice problems that we talked about last time, you guys probably get through 7 and 8 with what you found in part 1. But here, let me go over number 9 for you, and we'll have more card probabilities later. If one card is drawn from a deck, find the probability of getting these results: a queen, a club, a queen of clubs. Okay, so let's look at the probability of getting a queen. Now, I should show you before we do that. Let me come back to this, because I've referenced it, but I haven't really shown you yet. Let me come back to the slides here before we talk about that. Let me go. Okay, right here. Okay. Classical probability. Now, what is classical probability? Classical probability assumes that all outcomes in the sample space are equally likely to occur. Okay. So if I'm looking at, and cards is an example of classical probability, all right? So I'm looking at the number of outcomes that are part of the set that I'm interested in over the total number of possible outcomes there are. So here's my formula. Probability of the event is equal to the number of outcomes in the event space over the number of outcomes in the sample space itself. Okay, now that looks hard, but this is not actually that bad. Let's look at the sample space here. Now, if I'm going to do this, and I'll put this up, this is slide number 7, okay? On your, and this is your friend, so use this. Now, let me come back to this here. We're going to do whoops, I lost my, give me a second here. I need to pull up the homework one more time. So it says, if one card is drawn, let me share screen here. If one card is drawn from a deck, find the probability of getting a queen. Okay, well, all right, let's look at the first one here. So now, this is number 9 on your paper, all right? And so we're looking at 9A, which is the probability of a queen. So what we're going to do is we're going to say this capital P is probability of getting a queen. Now remember that my formula is the number of ways in the event, E, over the number of outcomes there are in the sample space, right? So what we're looking at here, and I guess I should, I'm going to do this. I'm going to say, before I write that, I'm going to write this. I'm going to say, all right? So this is my basic formula. The number of ways to get the event over the number in the sample space. Now, my event here, my event is drawing a queen. Okay. So how many queens are in the deck? Well, okay. So here, the number of the number of outcomes of the event, how many queens are here? You can pause the video at this time and think about how many ways to get the event and how many outcomes in the sample space, okay? You need these two numbers to make this probability. Pause the video and think about it. Okay, now, if you remember what we just saw a few minutes ago, okay, if I look at the number of ways to get the event, okay, if I look at my sample space for my deck, how many queens do we have? Well, we have a queen of clubs, a queen of spades, a queen of hearts, and a queen of diamonds. There are 4 of those. Okay, so I have 4 queens and I have a total of 52 cards. If you count, you'll find there are 52. There's 13 in each suit. So that means that we have this. We have there's 4 outcomes in the event, and there's 52 in the sample space. Okay, now, when you're doing these probabilities, okay, we're going to write it this way. We're going to say the probability of a queen is equal to 4 out of 52, we're going to reduce this fraction. So we're going to start with our fraction. We're going to reduce it if we can, which this reduces by 4. 4 divided by 4 is 1. 52 divided by 4 is 13. This reduces to 1 out of 13. Then we're going to make this a decimal, okay? So we're going to make it a decimal. So I'm going to go up here. And I'm going to give me a moment for my calculator to open so I can show you that. So now I'm going to clear the calculator here. And I'm going to stop sharing for a moment. And I'm going to grab the calculator here. Okay, now I have the calculator on the screen. And if I take 4, and I divide it by 52, okay? Before I convert it to a decimal, if you've already converted it, that's fine, but you can use your math, convert to frac, which is number 1, to get your reduced fraction. This is 1 over 13. And then if you want to convert that to a decimal, you can go 1 over 13. There's my decimal number. Okay, 1 over 13 is 0.07692. And you can multiply that by 100 to get your percentage. So the reason that I'm showing you this is because many times she'll want to see all 4 of these. Okay, so you want the original fraction, which is 4 over 52, the reduced fraction, which is 1 over 13, the decimal, which is 0.0769, and then you're going to multiply that by 100 to get your percentage. So that comes out to 7.69%. So let me write that down, okay? 0.0769, 7.69%. So here you'd have, this would be equal to 0.0769, and that would equal 7.69%. Okay, so you have this in 4 types. So you have it in the original form. Then you have the reduced fraction or simplified. Then you have the decimal. And then you have the percent, which is typically the way that she wants the answer. There are some exceptions, but especially with classical probability, that's how we do it. Let me show you another one here. Going to go to another one here. Let's do 9B, a club. Okay, a club. Well, how many clubs are there? And how many are in the sample space? So let's look. Okay, let's look at it. Clubs, remember, are the ones that look like black shamrocks. There are, let me count for you. There are, here's my clubs. This is Here are my clubs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 clubs, okay? Face cards count. It didn't say the ones that weren't. So there's 13 clubs. There's 52 cards. So again, when we come back here, we're going to say the probability, this is 9B now. So I'm going to move the whiteboard here. I'm going to say that the probability of clubs of drawing, I'll put 1 club, right? The probability of drawing clubs, a club out of the deck, right? Probability of drawing clubs is going to be the number, remember, it's the probability of the event is equal to the number of ways to have the event over the number in the sample space, right? So this is going to be probability of clubs. It's going to be 13 out of 52. And then you have you reduce the fraction, which is 1 out of 4. Then you go to a decimal, which is 0.2500 if you want to make it 4 places. And then you have your percentage, which is 25%. Okay. So something like that. That's the probability of drawing a club. 1 card from a deck. Let's look at, I'll do 9, whoops. I'll do the next one, which is a queen of clubs. Queen of clubs, okay? Well, how many queen of clubs do we have? Queen of clubs, not a queen of clubs. Well, there's only 1 queen of clubs. Let's find her. She's the queen of clubs is right here. She's the queen of clubs. There is no other queen of clubs. That's this only card. So there's only 1 card in our event space here. So here we're going to have this. We're going to say the probability 9C. We're going to say the probability of a queen of clubs is going to be 1 out of 13. And if I reduce that, let's look at my calculator, because our calculator is our friend, all right? So we're going to go to the calculator at this point. We're going to go 1 out of 13. Now this doesn't reduce. So we're not going to have that extra step. But this is the same probability as a queen because it reduced, remember? So we have 0.0769. So this is going to be this is going to equal, hold on, let me annotate this. So this is going to be equal to 0.0769. This is, we're multiplying it by 100, so we get 7 point, oops, this is equal to 7.69%. Okay, that's our percentage, something like that. Okay, 9D, let's do D. 9D says, what is the probability of a 3 or an 8? A 3 or an 8. So here, now this is our first introduction to what we call logical operators. When you see or, okay, when you see or, when it's related to probability, this means in one group. It can also apply to or both groups. Now, in this case, a 3 won't be an 8 and an 8 won't be a 3, but we can't always say that. Sometimes we have groups that overlap. This time we don't. So here we'd be looking at the probability. If I write the probability of 3 or 8, what I'm really saying is I have to find myself the probability of 3, and I have to add to it the probability of 8. So when you see the word, this brings up the first little inclination of what's coming later. We'll get into this in 4.2 and 4.3. But when you think of or, I want you to think, when it's related to probability, I want you to think addition when you see or, okay? I want you to think of addition there. So again, how many 3s? Let's think about this here. The probability of getting a 3. How many 3s are in the deck? Okay, how many 3s are in the deck? So let's go look at our sample space. We want 3 or 8. So here we want 3. 1, 2, 3, 4. There are 4 3s because there's 1 in each suit, right? So there's 4 3s, and there's 1, 2, 3, 4 8s, right? So it would be 4 out of 52 plus another 4 out of 52, different group, but still the same thing. So we're going to go here and we're going to say, all right, well, that means that this means that I'm going to write this. I'm going to say probability of 3 or 8 is equal to 4 out of 52. Okay, 4 out of 52 plus another 4 out of 52, different 4 cards, but still 4 cards, right? 4 out of 52. This is now going to give us probability of 3 or 8 is going to give us 8 out of 52. And if I reduce that, let's go grab our calculator because our calculator is our friend. Okay. I'm going to make sure I'm sharing the calculator here. So I have 4 out of 52 plus 4 out of 52, which you might know is 8 out of 52. Here's my percentage. Okay, they're my decimal rather, my decimal. If I want to know the fraction, I go, let me do the percentage first. So I multiply by 100 to get my percentage here. All right, which is 15.38. So then now if I want to convert this back, I go math. If I want to convert this decimal here back to frac math, convert to frac. Math, convert to frac. So here I have 2 out of 13. Okay. So what I would do is I would say that this is, I would write this as, I would write this as 8 out of 52, which I already have. This is, I reduce this by 4, so I get 2 out of 13. Then I have 0.1538, which translates to or converts to 15.38%. Okay, that's my deal there. So now I'm going to stop sharing this. And I'm going to go to, there's one quick thing that I'll let you do E by yourself, a 6, or well, no, maybe not, because there's a trick there. Okay, if really quick, I do the probability of 6 or spade, here we have an exclusion that we have to worry about, and I'll show you that. 6 or spade, okay? This is going to get into what we call overlapping events or mutually exclusive events, and I'll talk more about that in the next part of this video. But 6 or spade, so if I go here, this is going to be the probability of 6s, okay, not a problem, plus the probability of spades. But now we have something going on here that we didn't have going on in the previous question, okay? Now, in this case, the 6s overlap, okay? So let me show you something. The spades and the 6s overlap. So here, if I say, okay, I can find the 6s pretty easily, right? There's my, let me annotate this. And let me spotlight it for you. So here's the 6s. 1, 2, 3, 4. The spades, so let me draw here. The 6s are this column here. Okay, there's the column of sixes. Now, the spades are this row going across. So let me do the spades going across. There they are, right? There's my spades. Okay. Now, you see this card that intersects right here? If I do my probability and I say, well, there's 4 sixes, right? And then I go again and I count the 13 spades, then I've counted this card. I've counted this card twice. Okay. So what I have to do is when I count, I have to say, well, there's 4 sixes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. But I don't want to count this 6 twice. This 6 of clubs twice, or 6 of spades, excuse me, twice. So I want to remove 1 card. Okay, so what that looks like is this. What we're going to say is we're going to say probability of sixes plus the probability of spades minus the probability of 6 and spade. Okay, 6 and spade. So now six and a spade. Whoops. Let me make clear this part so I can write it properly. Okay. This is okay. This is going to be the probability of six and spades. Okay, or the 6 of spades. So this is going to be 4 out of 52. Spades is 13 out of 52. So this is 13 out of 52. Okay. Now here, remember I counted 1 card twice, which was the 6 of spades. So I'm going to remove 1 of the cards, 1 out of 52. And so I have 4 plus 13, that's 17, minus 1 is 16. This is going to give me 16 out of 52. And so then I'm going to say, I'm going to reduce it by 4. You can do this with your calculator and verify my work. This is 4 out of 13. Okay. 16 out of 52 is 4 out of 13. And that, if you do the work there for that, 16 out of 52 will give you 0.3077 if I round it. 0.3077. Here's the calculator for that. There's my calculator screen, 3077. So here, I'm going to stop sharing. This is 0.3077. And I'm going to leave this video here. I was hoping to get a little further than that. But I'll come back and talk more about how to deal with what we call overlapping events versus the ones that aren't. We have names for those. Those are mutually exclusive events and non-mutually exclusive events. We'll get into that more in 4.2. But for now, I'm going to leave this video here. I will bid you a fond farewell. Thank you for watching. And I will see you in my next video. Thank you very much.